permutations, combinations. You're going to constantly hear me call it perms and comps. It's lazy. So it's important that you know perms and comps mean the same thing, permutations and combinations. Before we start into permutations and combinations, we start off with pathways and fundamental counting principle, which is today. This is pathways. So if you read the question, it says, Mr. Kennedy is at his house, which is point A, here, and wants to walk to his house, to his parents' house, which is point B. How many different pathways can he take to get there? So how many different routes could I take? And if you look at it, it's like there's one pathway right here. Right? That would be one. This would be another pathway. That'd be two. And you're going to notice if you try doing it like that, you're going to have a ton of pathways that you can do. Like a lot of them. So trying to actually count and trace out the pathways isn't going to be the way to handle this, because it's just going to be way too many combinations of roads that you can take. Instead, we try to count our way and build our way all the way to where we want to go. Before we start building this, there's going to be an assumption made on all the pathway questions. The assumption is you are always headed towards your goal. So for instance, I couldn't be like, I go one to the right, one down, one to the left. I would never go left because that's moving away from where I want to go. So you're always moving in the direction that you want. Make sense? All right. The way to do this is to break everything into steps. So if I'm starting at A, how many ways could I walk to this next corner right here? How many ways can I get from here to here? One way, right? That's it. I can just walk one there. So go one way. And you're going to continue that all the way across the top. How many ways could I get to this spot? One. Walk straight across the top. One, one, one. That's how I could get to all those corners across the top. I could also do the same thing going straight down. So if I wanted to go to here, the number of pathways to there would just be straight down for a 1. I could go straight down again for another 1. I go straight down again for another 1. So the top edges, like the first 2 edges, are usually the easiest ones to fill in, because there's only one way to go across that top, one way to walk down that side. Where things get a little trickier is figuring out how we get to all these middle points on the inside. So if I wanted to talk about this point right here, how many ways could I get to that red dot? I could go to the right and then down. That would be one pathway. Or I could go straight down and then to the right. So there's 2 possible ways I could get into that spot. The next thing I could do is look at these dots. Green. How many ways could I get to that green dot? Well, I could go 1 all the way across, then straight down. I could go this way, across, down, across, for 2 different pathways there. Or I could go down, and then across. So that would be 3 different ways to get to that corner. If you trace out the pathways to this green dot over here, it's also 3 ways. You could go 1 to the right, straight down, down, over, down, or all the way down and then over. If you try tracing this out all the way across, it's going to get crazy. And it's going to be way too challenging to do it that way. But the reason we did the first few is to show you a trick. And that trick is how we're going to do this grid really quickly. This pathway of number 2 is the 2 paths connecting it added together. So 2 was 1 plus 1. This pathway of 3 was the two dots connecting it together. 1 plus 2. This 3 over here was the same thing. The two dots that it connects to added together. 1 plus 2. So that means if you take the edges on the corners next to it and add them together, that would tell you how many ways you can get to each spot. So for instance, so I wanted to get to this spot right here. It would be 6. It would be 3 plus 3. Because I could get to the spot above 3 different ways, the spot beside it 3 different ways, and those could join together to create 6. And you're going to do that to fill in this entire map. So that means this guy down here would be 4. This guy over here would be 4. And you can keep going along to each dot. So this guy right here would be 4 plus 6 for 10. This guy right here would be 4 plus 6 for another 10. This guy right here would be 4 plus 1 for a 5. And you can keep going. So if you fill in all those dots by just adding up the corners that lead into that corner, eventually you'll work your way to the end of the grid. And that'll tell you how many ways I can get from A to B. In this case, it's 56. Does anybody have any questions about that? Alright, over here on the side, you have a space to write out that strategy in your own words. The way I would write it out is add up the corners that lead to that path. But maybe you have a different way of telling yourself how you remember doing that. So if you're like, add one above and one to the left, if you're moving to the bottom right to the right, that works for me too. However you want to word it in your own words, I want you to describe what you're doing. Because that's a nice little space to keep it, and you can always reference back to it. So I would say, add the corners that lead to each spot. That's how I would describe it. To me, in my head, that makes sense. But maybe you need more detail to make sense of it. Yeah.
For the top half, is it 6 also? Because that's the 6 carrying one?
This is 6. This one? This is 6 because I could have done 1 all the way across and down. And I also could have gone to this spot 5 different ways. So it would be 5 plus 1.
Okay, when you look at it, it'll just like, if there's 6 big boxes, it has 6. You know what I'm saying?
Being like there's
After those
1, 2, 3, 4, 5. That's your 6th spot. You could, but you might just end up with a weird, because shapes will get a little different too. So I just worry that you might make a mistake on it. You could, because realistically all you're telling yourself is I went 1 down and then all the way over. 1 over, down, all the way over. So if you can see that, that's okay. It's these ones in here that are hard to see. It's hard to see the 35. Like, it's hard to tell all 35 paths I can get there. Because it's kind of crazy. Alright. Examples of this. Do one more with you, and do one more on it. So the first one says, after taking a bus to Calgary, Stedman is wanting to walk to the concert hall to see his favorite band. How many different paths could he take to the concert hall? Here's the bus station. Here's the concert hall. I need to figure out the different number of pathways there. I'm going to start off with the ways I know. So if you move 1 to the right, that's a 1. And that same 1 would be right next to it, and it would be right next to it. Because that's the only way he can walk across the top. He's never going to backtrack. The only way he can walk down the side is straight down. So all of those corners are 1s as well. Now I'm going to fill out the middle by adding up the corners to each one. So I want to get this dot to be 1 plus 1 for 2. Yeah.
So if we're doing the one next to it, is that we add up the 2 plus 1?
Yeah, so this is going to be 2 plus 1 for 3. Exactly. And you're going to do that all the way across until you get to this kind of weird intersection. We label it with blue. So count all the ways you get to that blue guy. And we're just adding corners. And if we complete that first box, I find that I have 35 different ways I can get to that little intersection spot, that blue dot that I've drawn in there. There's 35 ways to there. Hopefully you're all done that. That means if I want to walk to this spot right here, there was 35 ways to get to where they intersected. To go 1 more to the right, there's still only 35 ways. And there's still only 35 ways. So I've made all my ways to get to here. The only other possible direction is to go 1 right. There's no other way I'm getting to that spot. It's the same pathway I took to get to that spot. So it's 35. And going straight down would be the same idea. 35, 35. That's how those double ones come a little trickier. Now you can add up the middle again. This is where you might need to start using a calculator. This guy is going to be 70, 35 plus 35. This guy is going to be 105, 105. Finally, 210 ways. Alright, that's the number of ways Stedman could get to the concert. We're going to do one more together, and then I think you get a couple by yourself. Let's check. No, you don't. I want you to try number 2 on your own. So give it a shot on your own. Fill out the whole thing. This question says, after robbing a bank at point A, Becky must return to her safe house at point B. How many paths could she take to get there? Now you're going from A to B. So you're going up and to the left. If you counted down and to the right, it would be the same answer.
Okay.
Yeah. It would be the exact same paths, you're just going backwards. Yeah. Yeah, you can leave it. Okay, so in the green, it's going from point A to point B. And I got 120. We have a few different answers. So some people went backwards, so I'm going to check to see if it actually works the same. It should, but I just want to double check that. So I'm going to erase this, do it again in another color, go in the opposite way. If you count the other way, it does work, so that's possible. Alright, those are pathways, I call them grid pathways. Because it looks like a grid, it looks like a straight pretty much. The other type of pathways you do see is like flight pathways. So this is a question that's describing a flight pathway or a non-grid pathway where you kind of have looping things in the spots. This question says, Jenna wants to fly from Saskatoon to Winnipeg. The possible flights she could take are labeled below. How many different ways could Jenna get to Winnipeg? So if you look, these paths that they've drawn are different flights in different places. And there's no way she can get from Saskatoon directly to Winnipeg. It looks like they're making her stop in Regina, which if you know geography, it doesn't make much sense. But we don't know geography, so it's okay. Saskatoon and Regina are pretty close to each other, so maybe Saskatoon's airport's really small. We're going to go with that. Anyways, to figure this out, we're going to look at a couple experiments. So you could try counting them out. You could be like, all right, she flies route D, and then she flies route A. That's one possibility. You could also say she flies route, maybe a different color, D, and then route B. That's another possibility. Or she flies route D, and then C. That's another possibility. And you could try to count out all the combinations. In this one, not that challenging. That's because the numbers are small. Some of the other questions you're going to get, there's going to be more things and more pathways to figure it out. So what we do instead is we figure out how many different ways did she get from Saskatoon to Regina. Yeah.
Let's just multiply that number.
It's exactly what we're going to do. How many ways can you get from Saskatoon to Regina? There's only two ways there. You went D or you went E. There's two routes. And then my question is, how many ways can you get from Regina to Winnipeg? And there's three pathways into Winnipeg. So to figure out the total number of pathways from Saskatoon to Winnipeg, you multiply those two numbers together. So if you went 2 times 3, that would tell you the total number of ways from Saskatoon to Winnipeg. There was 2 different ways to get into Regina, and both of those pathways have 3 other pathways to get into Winnipeg. And these maps can get big, and they can cross each other in funny ways. If I was to describe that, it says over here, on-grid pathway strategy, so I want you to write out your own strategy on the side. I would describe my strategy as multiply the routes into the cities. That's how I describe it. That makes sense in my mind when I say that, because I know what's going on when I say that. You might need to write it out with different words, and that's okay. So I'm going to say multiply the number of ways into each city. And this doesn't have to be flights. So this could be ways of driving somewhere, walking somewhere, all kinds of crazy things. It's just you usually see curved things like this in flight paths. Like that's what you legitimately see when you look at flights in the paths that they take. They take arcs over each other.
So we did 3 if you want 2 times 3 is 6.
Yeah. So now Winnipeg was heading into Toronto, and there was 2 ways into Toronto. It would be 2 times 3 times 2 ways into Toronto. To tell me the total number of ways I could get across them. Alright, here is a grid. This is buses, I think. So Mr. Kennedy is stuck in Winnipeg and trying to take a bus to Saskatoon. Below is a diagram showing all the bus routes that could get him from Saskatoon, or get him to Saskatoon. How many paths could you take to get to Saskatoon? And you'll notice this is the same as the flight pathways. They're not nice arcs, but it's the same idea that you're branching off all over the place. So this would be a very realistic question that you could get on, say, like a diploma exam. They don't always organize things nice and perfectly. They like to put it into context of a real-life situation. Hey. Yeah, so, yeah, you only count where you can tell for sure it's passing through. So, like, Estevan isn't going to make a difference because the red path never goes to Estevan. No, we're going to talk about that because that's going to affect things possibly. So, I'm starting at Winnipeg. I'm going to try to get to Saskatoon. I'm going to try to figure out the number of different ways I could get to each city. The number of ways I could get to Brandon would be what? Just one way in, right? One right across. So I'm going to put a 1 there. The number of ways I could get to Yorkton. One way there. The number of ways I could get to Weyburn. One way there. You wouldn't backtrack.
You're going back.
Yeah. You won't backtrack. If you went like that, you could, but they don't have it highlighted. The number of ways that you could, because remember these are bus routes, right? Not just driving routes. The number of ways that you can get to Regina then is 3. I could go up through Yorkton to Regina. I could go through Brandon to Regina.
Yeah.
I go through Weyburn to Regina. Now I ask myself, if I was in Regina, how many ways could I get to Saskatoon? I could go up and over, or over and then up. So there'd be 2 ways to get into Saskatoon from the previous city I was in. Then you multiply all your possible routes. So in this case, you're going to have 2 times 3 times 1 times 1 times 1 for a total of 6 different ways that you could get from Winnipeg to Saskatoon. Did those ones make a difference? No, timesing by 1 is just like timesing by itself, right? It doesn't do anything. It's not like by itself, it's like timesing by nothing, which isn't also true. Semantics. Problem.
You don't have to multiply like the amount of towns.
No, so and that's the good point, is it doesn't matter how many towns I went through, all that matters is the number of ways I got to Regina. So there was 3 ways there, and I went through Yorkton, Brandon, and Weyburn, but those routes really made no difference because there was only 1 way into Weyburn, 1 way into Brandon, and 1 way into Yorkton. So if this was me, I wouldn't even worry about the Yorkton, the Brandon, and the Weyburn. I would have been able to recognize when I look at this thing that I go from Winnipeg and then things come back together at Regina. That's the only other place where they all meet up.
That little branch, that little fork right now in Winnipeg.
Here?
Yeah.
How many ways is there?
Oh.
Yeah, but that's why. If you had gone the other direction, that would make a difference. Because there's 2 ways into that conjunction.
So then we could still get the same thing.
It would still be the same. Well, yeah.
Maybe 2 ways in Winnipeg then?
Yeah. 2 ways into Winnipeg, 1 way in that spot. Yeah. Yeah. It wouldn't be the same.
Maybe 2 and 2.
Yeah. Because you're going backwards, right? You could have come together in that spot. So direction would matter on that one. So you multiply your routes into cities when you're doing non-pathway questions. Here's 3 more examples of non-grid-like paths. I want you to try all 3. Okay, let's talk about diagram 2. So diagram 1, there's 5 ways into B, and there's 3 ways into C. So at 5 times 3, and that'll give you an answer of 15 ways from A to C. Diagram 2. I've already labeled the top way, so there's 3 ways into B1, and then there's 3 ways from B1 to C. Along the bottom, there's 3 ways into B2, and then 2 ways into C. Before, what we were doing was we were multiplying our routes to figure out the total number. That's going to work in certain circumstances. So, for instance, if we look at this diagram number 2, and we pretend that the top doesn't exist, and we're just going to go from A to B2 to C. How many ways can we go from A to B2 to C? 3 times 2. There's 6 ways, right? You multiply. 6 ways from A to B2 to C. Now if you ignore the bottom, how many ways is there from A to B1 to C? 3 times 3 would be 9. Now the reason we were multiplying and everything before is because the pathways all went through each other. So for instance, in diagram 1, we had 5 and they all came to here. And then each 5 of those had 3 options out. That's why we multiplied them together. On diagram 2, I had 3 ways into B1 and then 3 ways into C from B1. So I multiplied those together to get 9. If I went down, I got 3 and 2 for 6 ways. But would these 6 ways be affected by any of the choices on the top that were made? No, they're completely separate, right? If I go this route, and I draw in red, straight through, and up, I'm never going to use any of the routes up top. So those top routes aren't going to be multiplied by me. Instead, what I'm going to do is I'm going to add the 2 possibilities together for a total of 15 routes. So I could go 6 ways through the top, 9 ways through the bottom, for a total of 15 different ways. You wouldn't multiply them together because any path you choose on the top wouldn't happen at the same time as the path at the bottom. Right, now you can try diagram 3. Alright. If we did this one, I did it in 3 colors. Red, green, and blue. If I go the red way, there's 1 way into B1, 3 way into C. That's 1 times 3 for 3 going across the top. Across the middle would be 2 times 1. Across the bottom would be 3 times 2. You add all the results. The total should have been 11 pathways. Okay, those are the pathway questions. The second part of this lesson is called Fundamental Counting Principle. And this is a way of quickly counting things and counting possibilities and outcomes. You're going to hear it referred to a few times, and that's okay if you're like, what the heck is it? It's just your way of counting and figuring out how many options there are. It's a method, that's all. Here's an example. Mr. Kennedy is cooking burgers for his family and allows each of his family members to choose one of each item for their burger. They can choose from 2 different meats, 3 different condiments, and 2 different vegetables. What's the total number of combinations of burgers that could possibly get made? The way we used to do this was a tree diagram. So if you look, you could say, well, at first you chose a meat. You chose meat 1 or meat 2. After you chose meat 1, you had 3 options. You could have done condiment 1, condiment 2, or condiment 3. After you chose a condiment, you had 2 options for a vegetable for each one of those. And we said that if you followed the branch, that would be an outcome for every single one. So you could have M1, C1, B1, or M1, C1, B2, or M1, C1, C2, B1. And you would fill out that whole chart. And it was a lot of work, wasn't it? When we did it with our heads and tails or our spinners, it was a lot. And those tree diagrams are good. Sometimes they're easy. But as these questions get bigger, they become more complex. So instead what you use is the fundamental counting principle to tell you how many outcomes there are. It won't tell you what each outcome is. The tree diagram does that. But you can figure out how many possible burgers there are. Yeah, you're only allowed 1. I'm cheating.
It's not going to fly.
It's not going to fly. You're not welcome to my burger joint, I guess. The fundamental counting principle, I do it like this. I draw little lines. The first line represents my meat. My second line is my condiments, which I'm just going to call con. My third option is my vegetables. Oh, okay. And those are placeholders, those lines. They're placeholders for how many options I have for each thing. So how many options do I have for meat? How many options for condiments? How many options for vegetables? I can choose from 2 meats, 3 condiments, or 2 vegetables. And if I multiply those together, that'll tell me the total number of combinations I could have. In this case, there's 12. It's called the fundamental counting principle. You put placeholders in, and then you fill out the number of possibilities for each placeholder.
Why couldn't you have told us this last year?
Because last year you had to know what each outcome was. That was why we were doing tree diagrams.
Oh.
This doesn't tell me that it's possible to have chicken with mustard and onions. I'm taking out with the worst possible combo I could. That's pretty gross. Right?
Mustard.
Where the tree diagram, like, it told you all the outcomes. Alright.
There was no chicken, just vegetables.
Examples of how this goes. Because these get confusing, they get big. Example 1. How many ways can Mr. Kennedy make a 4-number password on his iPhone? There's 4 spots. 1, in mine I'm only making a 4 digit. 1, 2, 3, 4. Each represents a spot in the passcode. How many numbers could go in the first spot? I have 10 options. And 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different options that could go there. How many options could go in the second one? 10, 10, 10. So if you want to figure out the total number of combinations, you multiply those together. So the total number of combinations would be 10 to the power of 4, which is 10,000. You need to understand that it can be written as 10 to the power of 4. Or 10,000. Both answers would be valid and could pop up on a test.
Yes.
Yeah, well, yeah.
Yes.
10,000 times, yeah.
But
And if it's 6,
up to 60 if you want.
so then you're actually guessing a billion answers.
But faster. I'll just figure it out.
Example 2.
Whatever's on your phone.
Francis is baking a 3-tiered cake. For the top layer, he can choose between pink, blue, or green. The middle layer, he can choose between blue or pink. And on the bottom layer, he can choose between black, white, orange, yellow, or green. How many different cakes could he bake? Put 3 spots. That's the top tier. Middle, bottom. Those are my 3 placeholders. How many possible colors was there for the top? 3 goes in that placeholder. There was a possibility of blue, pink, or green. So 3 colors. The middle tier, he has between blue or pink. 2 options. And the last tier, he has black, white, orange, yellow, or green is 5. To figure out the total number of cakes he could create with all the combinations, you multiply these together to get 30. So he can create 30 different looking cakes using that setup. Example 3. How many ways can Mr. Kennedy make a 10-number password on his iPhone if he doesn't want to repeat any numbers? That's going to be important. Doesn't want to repeat any numbers. So what I'm going to do is put a placeholder for each spot. So I'm going to have 10 different spots with a 10-number password. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of numbers that could go in the first spot is 10. I put 10 different things in there, 0 through 9. The second spot, though, since I can't repeat any numbers, means it can't be the same as whatever went in here. That means I only have 9 options left for that second spot. Because I already used one of the numbers and it said I can't repeat. If we continue with that trend, the third spot, I would be down to 8 numbers left to choose from. And I'm going to do that all the way across like that. Every time losing one number. If you put that in your calculator, all multiplied together, that'll tell you the total number of ways in which you could do that. Yeah, the answer is 3,628,800. A 10-number password?
We put 3.6.
Think of it as your phone number. Phone numbers are 10 digits long, right? Yeah, except we can repeat numbers and stuff. So if you ever want to figure out how you're going to run out of phone numbers, you would put in 10 blank spots and then 10 for each number because you can repeat. So the total number of phone numbers is like 10 to the power of 10, which would be a lot of phone numbers. But that's not realistic because there's certain numbers you can't have, right? You can't start with 8 or 911. Like that can't be a combination as the first 3 digits to a phone number, or else it automatically calls it. You can't start with the number 0, or it calls the operator. So there's like certain rules. Yeah, still a lot. Even when you break it down to like, if you know you are always going to have 403 as your first 3 digits, and then 948 is your next 3, you still have. Yeah, you still have 4 digits worth like 10,000 or whatever it is, combinations, knowing the first things.
Depending on where you are, you can start by
Yeah. This right here, this combination of like 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 isn't going to be a rare thing that happens to you. It's going to happen a lot. It's got a special name. When you have all numbers consecutively like that multiplying from 10 all the way down to something, or maybe from 20 all the way down to 1, it's called a factorial. And you could write that in your calculator so that you don't have to actually calculate it. The factorial symbol is an exclamation mark. So if you turn over to the next slide, they'll tell you all about factorials. So it says, in example 3, writing out 10 times 9 times 8 all the way through is a time-consuming process that can be made easier by using a factorial. Instead of writing all this, you could just write 10 exclamation mark. And that is a button in your calculator that we're going to show you. It works, yeah. For instance, that was 10 factorial. If I wanted to know what 6 factorial was, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, all the way down. Or if I wanted to know what 13 factorial was, that's 13 times 12 times 11 times 10, all the way down to 1. The factorial button is in your calculator if you hit math. And then you click the arrow over to PRB. So you click it 3 times to the right. It'll be your 4th option. So if you wanted to do 10 factorial, you would go 10, and then math, over to that exclamation mark, hit it, hit enter, 3,628,800. It is in your calculator. A good way to help yourself remember where it is, PRB stands for probability. So all your probability options will be under that heading when you go to math. All right, example 4. If 30 grade 2 students need to stand in a straight line before leaving class, how many ways could they stand in line? Well, picture it. If you had 30 spots that each kid could stand in, you drew them all out. There's 30 of them, that's a lot. How many kids could sit in that first spot? You could pick from 30 to go in that first spot. How many kids would you have left to pick in the second spot? 29. How many in the third spot? 28. And if you wanted to draw that out, 30 all the way down to 1, it's going to take a long time. Instead, what we say is that there's 30 factorial ways for those students to line up. Your calculator probably can't do that number. If you try it, it's probably way too big. Yeah, it's 2.65 times 10 to the power 32. So it's way too big of a combination. So that would be your answer right there, 30 factorial. You wouldn't actually calculate it and write that number out.
What number do you limit that at? Like, that's all.
Yeah, whenever it's going to go like that, and that's going to happen a lot. That's another big part of the fundamental counting principle is these factorials. All right, examples. You're going to notice there's a lot of word examples. So this one is an example of a word example. It says, how many ways can the letters from the word hockey be arranged? They don't care how you arrange them. It doesn't have to make another word. They just want to know how many ways could you arrange it. To figure that out, you're going to use the fundamental counting principle. How many letters are there? That means there's 6 placeholders. And you need to put a letter into each spot. How many different letters could go in the first spot? 6. You can pick from any of the letters at that point. How many letters could go in the second spot? Only 5, because we've used one of the letters in the first spot. How many letters go in the third spot? Now you're down to 4, because you've used 2 of the letters out of the 6. So there's only 4 left to choose from. And again, you can count all the way down. That's like saying 6 factorial, which I think is 120. 700. Just, you know, 6 So there's 720 ways you could arrange the letters in hockey. I learned something neat when I was making these notes, and that is that the word uncopyrightable is the longest possible word without repeating any letters. So uncopyrightable has no digit letters the same. I googled this. That's how I found out. Because I wanted a big one with no repeating letters. You'll figure that out. Because when you have repeated letters, it screws
It always has to get harder.
Always has to get harder. Okay, I want you to figure out the number of ways that you could sort the letters in uncopyrightable. $50 letters there. So if you were to do that, you have 15 letters. That means you have 15 slots to place those letters in. And you need to go 15 times, 14 times, 13 times, 12, all the way down until you've used every letter. Put that in your calculator and it's not going to give you an answer that you like. Instead, what you do is you just call that 15 factorial. Example 7. Mr. Kennedy needs to make a seating plan for the 25 students in his class. How many seating plans could he create? So you imagine there's 25 desks. I need to fill each one with a different student. That means there's 25 placeholders, 25 things to go into each spot. You could draw each spot out, fill each spot in. It's not a bad idea, but for a question this big, it might be just why is to recognize 25 spots is 25 factorial. You could draw it out. It would still work out. What you'll notice if you try to go do practice on this stuff is that every question we've done so far has nothing the same. So, for instance, the word hockey didn't have any two letters the same. Then the word uncopyrightable, no letters were the same. When we were organizing students into seats, none of those students were the same student. They're all different things. Twins are still different people. There's half people. Even when we went back here and we talked about this right here, we had a password. Notice what said no repeated numbers. It purposely said that so that we had to use factorials and that we could use factorials. Tomorrow things will change. I'm